Swayam Prabha. Digital India. Educated India.
Okay, so we talk about another public key crypto system which is called ElGamal crypto system, and this is based on the discrete lock problem is hard. So let us define the discrete lock problem. Discrete log problem over logarithm problem over. We have seen this in Diffie-Hellman key exchange. So problem is let P be a prime if P be a prime, then ZP star, which is basically ZP minus 0, this will be a cyclic group, and then let alpha be a generator of this group, alpha be a generator or primitive element of ZP star. Okay, then given this, then we compute beta, which is basically beta is alpha to the power a mod p, where a is 0 less than equal to a less than p minus 1 or equal to p minus 2. Okay, so problem is discrete log problem is given the value beta, alpha and p, given this we need to compute, need to find a. So this is the problem, this is called discrete log problem. So given beta, so this is sort of, I mean, if all are integer, this is sort of a real number, this is sort of log of beta base a kind of thing. So this problem is called discrete log problem. Given alpha, beta, beta alpha p, we need to find the a. So so the brute force method is we can try for all possible a. So we know a is from 0 to p minus 1. So we choose first 0, then we compute alpha to the power 0. We check whether this is beta or not. We choose a is equal to 1 like this. So this is exhaustive search or the brute force method. So the time complexity for this, time will take the time of the, I mean, order of the this prime number. So if p is large, then the discrete log problem is hard in this. So if p is large, then the discrete log problem is hard. Problem over ZP star is hard. That means it is not trackable. In this is intractable. Okay. So this is the discrete log problem, and we have seen the Diffie-Hellman key exchange protocol is also based on the discrete log problem. Now this public key ElGamal is based on this discrete log problem, and based on the hardness of this problem, discrete log problem is hard. Like RSA is based on the hardness of the factorization. If we have given a prime which we know that it is product of, if we given an integer which we know it is a product of 2 prime, now to get that PQ is hard, n is equal to PQ. So that is the hardness for RSA. Now here hardness is the hardness for this discrete log problem. Okay, so let us just talk about ElGamal crypto system. So this is a public key crypto system. So one has to generate the public key private key pair in order to receive the message. ElGamal okay, so the same story. Alice wants to send a message to Bob. So Bob is the receiver, Alice is the sender. So Alice needs to get, this is the public key setup. We are at public key setup. So Alice wants to get Bob public key in order to encrypt the message. So this setup has to done by Bob. So Bob has to generate his public key private key pair. So what Bob will do? Bob will first choose a large prime. Choose a large prime P such that discrete lock problem. This is the ElGamal crypto system over ZP or ZP star. Okay, so Bob choose a large prime P such that discrete lock problem is hard. Is hard in ZP. Okay. So then ZP is a ZP star is basically ZP minus 0 is a cyclic group. Now, so it has a generator. So Bob will choose the generator. Let alpha be the generator or primitive element, generator or primitive element of ZP star. So it will generate the groups. So alpha square like this. This is cyclic group in multiplicative sense. Okay, so now Bob chooses secret. Choose a secret A. A is lies between and Bob compute alpha to the power beta, which is basically alpha to the power A mod P. Okay, so this is the setup phase. So now, so after this, Bob is so the keys. So the key space is basically. So the key space is basically P alpha A beta, where beta is congruent to alpha to the power A mod P. So each key is basically having this part P alpha A beta. So among this is the secret key. Secret key or the private key of Bob, and the remaining this P alpha beta, this is basically EB. So this is the public key of Bob. This is the public key of Bob, and this A is the private key of Bob. So Bob compute EB, which is basically E alpha beta, and DB, which is basically A. So A is the secret key of Bob. So Bob send this EB over this public channel to Alice, because Alice wants to send a message to Bob. So Alice needs to get Bob public key in order to send a message to Bob, encrypted message to Bob. In order to encrypt the message to Bob, in order to encrypt a message for Bob. Okay, so this is EB, which is basically P alpha beta, which is the Bob's public key. Okay, now what is the encryption? And for encryption, so for encryption, what Alice is doing, on top of it, Alice is choosing a secret, a random number. This is Alice is doing. Okay. So before that, what is P? P is basically ZP star, the plaintext space, and C is ciphertext piece is basically, ciphertext has two parts, Y1 and Y2. It is basically ZP star cross ZP star, and key is this key space. It has four tuple like this. Okay, so the encryption is as follows. This is the ElGamal encryption. So for encryption, first Alice will choose a random number. Choose a random number. Random number k from ZP minus 1. This is the extra bit of secrecy. So this will, okay, so this is nothing to do with the key. So this is a extra, this is a random number Alice is choosing, and this is not known to Bob. So this is maybe after choosing the message, Alice choose this. This is sort of maybe some timestamp nonce it called. Anyway, so now Alice will encrypt the message X. So X is coming from ZP star. This is the message. This is the message. So this is the encryption. So Alice is encrypting the message using the Bob public key EB and using this K. So K is another input, this randomly chosen, and it has two parts. Message is having two parts, Y1 and Y2. Right, ciphertext has two parts, Y1 and Y2. That's why the ciphertext is the Cartesian product of ZP star cross ZP star. Okay, so what is Y1? Y1 is basically, okay, let me write here. So this is Alice is doing. So Alice is sending this Y1, Y2. Now what is Y1? Y1 is basically alpha to the power k mod p, and Y2 is basically x into beta to the power k mod p. So these both the values Alice can calculate, because Alice is choosing this k randomly. Alice is having alpha, which is the public key part of the public key of Bob, and that p is also public. X is the message Alice is chosen, and beta is public. So Alice can compute beta to the power k mod p. So this is the way we are masking the key. This is called masking the plain text. This is okay. We are masking the plain text. Now, yeah. So now this is the encryption. So this is the ciphertext C. So this is sending over the public channel to Bob. Now how Bob will decrypt it? So Bob is getting this message. Bob is getting this ciphertext, and upon receiving this ciphertext, Bob has to get back the message X. So how Bob can do that? So that is called decryption, ElGamal decryption. Okay, and this has to be done by Bob. ElGamal decryption. And this has to be done by Bob upon receiving this Y1, Y2. So Bob is receiving Y1, Y2. So what Bob will do? So decrypt of Bob has to use his DB Y1, Y2. So this is basically Bob will compute this Y2, Y1 to the power A inverse mod p. This is the decryption this is the ElGamal decryption. So Bob will simply compute y1 Bob is receiving y1 to the power a is the secret key of Bob. Basically, so Bob can compute y1 to the power a, then Bob will get the inverse, and then Bob will multiply this with y2 and take the mod p, and this supposed to give us the message x back. So we have to verify that. So what is the guarantee this will give us x? So this is because see y1 is what? Y1 is basically this one. So y1 is alpha to the power k. Actually Bob is not knowing k. Without knowing k, Bob should able to decrypt it. That is the beauty of this cipher. And so Bob is, so y1 is this mod p. Now what Bob is doing? Bob is doing y1 to the power a. So which is basically alpha k to the power a mod p, which is nothing but alpha to the power a to the power k mod p, which is basically beta to the power k mod p. Okay. Now if we, now y2 is also, what is y2? Y2 is, so basically we are doing the y2 into y1. So if you take the inverse of this, so y1 to the power, so y1 to the power a inverse, this will give us beta k inverse mod p. Okay. So beta k inverse mod p. Now if we just put it here, so this is basically x into beta k and then beta k inverse mod p. So this will give us basically x, the message or the plain text. So this is the decryption. We are getting back the message x. So x is the message we are getting from this. Yeah. So yeah, we can just write this side. This may not be visible there. So basically it is basically x into beta to the power k into beta to the power k inverse mod p. So these two are cancelling out, it is basically x mod p. It is basically x because x is coming from zp star. So Bob is getting the plain text. Now without knowing the k, without knowing this extra, I mean randomness in the ciphertext given by the Alice, without knowing the k, Bob can able to unmask this by this way. So this is the beauty of this cipher, and this is not a deterministic algorithm, this encryption, because we are having a this random k. So this random k, for this random k, many ciphertexts, this is not unique. I mean, for a given message, the ciphertext is not unique. So because random k is involved, so this is not, this is non-deterministic, because ciphertext depend on the both x and the random value k chosen by the encryptor or the sender. Okay. So there will be many ciphertexts that are encryption of the same plain text. So that is the non-deterministic crypto system. ElGamal crypto system is non-deterministic in that sense. Okay, so now let us take a quick example. We want to take a quick example how it is working. So we want to take some values. Okay, so this is the example of ElGamal crypto system. Crypto system. So this is again we have to run the setup phase. So Alice need to get his plain text and ciphertext pair, so that Alice can Bob need to generate his plaintext and ciphertext pair, so that Bob can make it public. It's Bob has to generate the public key and private key pair and can make the public key public, so that Alice can encrypt the message using the Bob public key. Okay, so this setup has to be done by the receiver. So this is the setup phase. So we need to choose a prime. So let us choose a prime, say 2579, provided this discrete log problem is hard, but this is very small prime. Anyway, this is an example. Now we choose a generator or the primitive element. So 2, we can check 2 generates the ZP star here. Now Bob chooses secret A, which is the secret key of Bob. Say this is the private key of Bob, private key. So this is public, this is also public, okay, and this is private, A is private. Okay, now we have to calculate the beta. So beta is basically alpha to the power A mod P. So this is basically 2 to the power 765 mod 259. So if we calculate this, this will give us 949. Okay, so this is the this is beta. So now Bob has both the public key and private key pair. So EB is basically all this component. So this beta is public, this is also public. So only secret is that A. So this is basically P, then alpha, then beta. This is the public key. P is basically what? P is 2579 and alpha is 2 and beta is 949, and the secret key of Bob is basically A. Bob is chosen as, so this is just A, which is basically Bob is chosen by this, and Bob makes this public, this EB over the public channel or in the public key directory. So Alice is having this EB, Bob public key, because Alice wants to send a message to Bob. So Bob needs to run this setup phase in order to get his public key private key pair. Okay, so now suppose Alice wants to send a message to Bob and the message is say 1299. This is the message Alice wants to send to Bob. So now Alice has to choose a random number which is K. So suppose Alice is choosing K, say 853 randomly. This is Alice is chosen. Alice choose this K. Okay, then Alice encrypt the message using the Alice encrypt this X with this K using the Bob public key and generate Y1, Y2. This is the ciphertext C. So what is Y1? Y1 is basically Y1 is basically we know alpha to the power K mod P. So here alpha is what? Alpha is basically 2. So it is 2 to the power K. K is basically this value, this random number Alice is choosing, 2 to the power mod P. P is basically 25. So if you calculate this, we will be getting 435. 435. Okay. So now So now the question is how to, so now how to get y2? Y2 is similarly, so y2 is basically masking x with the beta to the power k mod p. So x is basically this one 1299 into beta. Beta is basically this value 949 to the power k. K is the Alice randomly chosen value. This mod p. P is basically 2579. So if we calculate this, we will be getting the value y2 as 2396. Okay, so this is the y1, y2, and this is the ciphertext. We send it to the Bob. So this is 4352396. This we send it to the Bob. Okay, so now this is upon receiving this ciphertext, Bob has to decipher it. Bob has to get back the message. So now we have to run the decryption algorithm. So this has to be done by Bob upon receiving the ciphertext. So decryption. Okay, so for decryption, what Bob will do? So this is Bob is having Bob's secret key DB, which is basically A, and this is y1, y2. So Bob will calculate this y1 to the power A. So y2 into y1 to the power A mod p, and that will give us a x. So what is y2? Y2 is 2396 and y1 is 435, and A is basically what? A is the Bob secret key, which is 765, and then this is this inverse of this mod p. P is basically mod, this whole mod 2579, this whole mod 2579. Okay, so this may be out of the board 2579. Okay, so this we can calculate easily. I mean, if we calculate this inverse and all these things, it should give us 1299. So 1299. So this is the plain text. So this is the plain text which was encrypted. So see, without knowing the value k, which is the random value chosen by the Alice, Bob able to decrypt it. So that's the another level of security in this crypto system. We can, so this k is basically sum total of times tab or nonce. So this makes this crypto system non-deterministic, because for different values of k we are getting the different ciphertext for a given plain text. Okay, thank you.